Okay, it's a pleasure to have our own Andreas Wieser, who will tell us about quadratic representations of quadratic forms.
Thank you so much. It's always a pleasure. Okay. So everything I'm going to talk about is joint work with Wooyeon and Kim. Yes. And Pengyu from the Chinese Academy of Sciences. Right. And yeah, so it's a fun project we've been working on for a while. Happy to report on it. So let me just dive right in and just tell you what the representation is. Okay, so we have two quadratic forms. Both Q, Q, and PQ are two quadratic forms. Integral, meaning of integer coefficients. And maybe I'll give you some notation for the variables with m and variables. Okay, so I have a little quadratic form, fewer variables than a big quadratic form. And what does it mean to represent one by the other? So representation for me, at least for this talk, let's say, it's going to be the following. It's going to be Q by VQ. It's going to be a couple of vectors. There's a tuple. Vectors. Okay. Be add means to the n. Okay. So I have n vectors in n-dimensional integer lattice. And so that quadratic form, so I'm thinking of this as a lattice, right? And on this sublattice, my quadratic form, big Q, right, which is defined on Zn, okay, it's going to be the little quadratic form. Okay, so just to spell this out. X1 M is going to be the big quadratic form restricted to this sublattice. Okay. And right. So the basic question that we're going to ask whether or not such a representation exists. Okay. It'll be slightly more convenient for me. Let me add something here to look at primitive representations. What is a primitive representation? Its representation is primitive whenever the lattice is primitive, okay, which is to say that use the same color. That when you look at that is explained by vectors, this is the same thing as the points in rational subspace by vectors. Okay. Good. Just for convenience. Okay. Okay, so let me just spell out a couple of special cases. The first thing,
convenience, right? It's not just convenience. It's what allows you to
avoid. But I mean, there's results in either. Yeah. In fact, it's not really. Yeah. I don't think there are nice things to be. I can't say yet, but in primitive representations. Okay. So, right. Yeah. The first thing you should do. Right, we have two choices in variables, is you should take meaning the quadratic lib q here is a single variable quadratic form, right? Something like this, right? And then a representation of lib q by big Q is it's the same thing as a representation of the integer a, right? By big Q. Supposed to be an A. Yeah, my handwriting sometimes is a bit takes some getting used to. Sorry about that. I'll give my best. So, all right. Suppose that you have two variables. And then let's just write coefficients for this quadratic form. It looks something like that, right? And what you're trying to do is you want to find vectors, right? V1, V2, so that, well, you want to know the quadratic value of both vectors. Think of it, this is the length, and at the same time, you want to know the inner product. Yeah? Okay. So as a variety, this is already quite a bit more complicated. Right. Is it P or P2? It's P2. Thank you. Yeah. Good. Okay. So as I said, so we want to figure out whether or not we can find a representation. In particular, of course, particularly for this question of representing integers, this is a very classical problem, right? So, for instance, if let's say you have Q to be the sum of three squares, right? Okay, then some integer A is primitively represented as PQ, right? Where this primitively represented means that there is a primitive representation. If and only if A is not congruent to 0 for certain rate, we use a very handy criterion. In some sense, what we're trying to do is to find something. Right? Maybe for some strange reason you don't care about sum of squares, like to take it into quadratic form. This problem might become more difficult. Okay. So here's the first observation. Maybe I'll put here. It's a trivial one, okay? So if little q is primitively represented by big Q, if I can find such a sublattice, then obviously it is also primitively represented locally. Okay. Meaning that I can find such vectors, let's say mod n for an integer n, okay, or equivalent to ZP. Yes.
So do you say little q is primitively represented by big Q if all of the values of little q can be represented by big Q?
No, that's not the same, right? If I can find such a primitive representation, that's what I want to do, right? So once again, I'm trying to find a.
Why don't you write Ziegler notation? X transpose AX equals,
We can do that too, yeah.
and then everybody has matrices.
Yeah, let's do that for a minute. So, for instance, yeah, that's so. Like if you think so, I have little q, I have big q. If you think of little q as a symmetric matrix, right? Where off the diagonal I have half integer entries, but okay. And so what I'm trying to find is matrix, right? Which is in this notation here precisely the matrix of columns Z1 of the Vm, so that AX X transpose is what you meant to. That's the same.
That's easier to read than Siegel's Gothic.
Yeah.
That's the whole. But he writes it that way, and when he wrote his mass formula, he writes it that way. He proved, yeah.
Yeah, it's really in mass formula. Somehow, yeah. I like to think of subspaces. So,
No, they're the same thing, but
it's the same thing.
he asked the question. I'm sure now he knows what you do.
Does that answer your question?
Okay.
Yeah.
I think I'll pick up.
It's good to keep in mind these examples, right?
Right.
Okay. Good. So, okay. So in other words, right, if I can find, so what we're saying here is that if I wanted to find little q as a restriction of my BQ to some subspace, this is what this condition here turns out as well, then I need to be able to do it locally, right, over CP for everything. And so the local principle would like to say the converse, okay? Is it true that whenever Q is locally primitively represented, then it is, well, globally primitively represented? Yeah. Of course, so if you particularly if you keep in mind this the special case when I'm representing integers, right? This might sound very related to the Hausdorff-Minkowski theorem. Yeah, which is saying something very similar, but instead of looking at integers, we're looking at rational numbers. Okay, what does it say? It says that I'm thinking of quadratic spaces, right? So I have a quadratic space. These two quadratic spaces. Okay, so it's a vector space again of quadratic form, and I want to represent one by the other. So we'd like to find an isometry. Like so, okay? And I can do that whenever I can find one loop over QP for every P and over the loops, right? Okay.
So what does the arrow mean now exactly?
It means it's an isometry, right? So in other words, it's a map from QP to from Q to the M into Q to the N, right? So that the quadratic value, well,
Okay.
after taking the map, is the same as the quadratic value with respect to Q before taking the map. Or maybe if you want to spell this out in the case of representing numbers, right? You're trying to solve an equation like so. Okay. And so what you're saying is that this has a solution over Q whenever it has a solution over QP for every P in the overall. Okay. Okay. Good. Right. Of course, this means something for us as well. Namely, figure out how visible this angle is again. Right. We started over here. Okay, so the relevant notion here is the notion of genus, which is the set of all quadratic forms Q prime. Okay, so I have my quadratic form Q with integer coefficients, and I'm looking at all quadratic forms that are locally equivalent to that Q prime. Okay, where locally means something very similar to what we just had. Namely that if I can, basically I want to be able to, over every ZP, I would like to be able to change coordinates so that I get from one to the other, right? Yeah. So what you should think about here is, I should think of this genus, okay, as a quadratic form Q, okay? And a couple of friends. Now, 10, let's say, okay, these are not equivalent over integers, but globally equivalent. And so what does Hasse-Minkowski tell me? Hasse-Minkowski asserts from me that maybe I can't represent my quadratic form by little q by the big Q, okay? But I can represent it by one of these forms, okay? If I can do it locally. So let's say this Q10 here represents my quadratic form. But of course, the question we'd like to answer is whether my quadratic form BQ represents quadratic form, which this doesn't tell me yet. Okay? But in some sense, the task is to upgrade this statement to what we're aiming for here in this local global case. Okay. Yeah. Okay, so maybe let me move on and just tell you what we do know. And let me start by telling you what we do know for representations of numbers. Okay. So that is numbers. So that there's a distinction, of course, depending on how many variables I'm assuming might be quadratic formats. Okay. There's at least 4 variables. And this goes back to, so then the local global principle is answered affirmatively. I should say, there is one thing to be added here, that if classical statement is the fact that, well, going back to Eichler, is that if Q is indefinite, then the beam is like, it turns out to be trivial. But if you look at back here, in particular means that this statement is in the picture, right? So we're going to be focusing on positive definite quadratic forms this time. Because
The spin genus,
the spin genus is trivial.
not the
Yeah,
genus.
not the genus.
That can be very painful.
I was, it can be very, yeah, indeed. That's very true. Yeah, sorry, I was already thinking of this case. You're absolutely right.
3 or more variables. 3 or more variables.
Yeah. Right. In that case, we're going to be thinking about positive definite forms. Maybe at the very end, I'll explain to you why that is. It's a specific curiosity there. Okay, so try to represent the number A, right? And the local group principle is either be true if A is large enough. This goes back to close to for the diagonal forms. Tarkovsky for diagonal forms. This is based on the circle method. And not. Yeah. And I should say that what large enough means here is an effective statement, as opposed to what I'm going to write next. Okay. So n equals 3. So maybe let me add years here. Illustrate the thing. So this is from the 1920s. The problem for in 3 variables turns out to be much harder. And I'm going to lie to you here for a second, basically to swipe under the rug what Peter was complaining about. So let me just say that it's a similar statement. Okay. Yeah, statement. Which is due to so Yukonibanians, then also Yukon's appeal. And fields the fifth Shapiro. So look. And right. So similar statement.
You're working here with Z, right?
I'm working with Z.
We only did that.
It's number fields. Yeah, I'm aware.
Right. Yeah, and there could be a square class that's omitted.
This, yeah. So.
Okay. All right.
I want to explain that actually at some point today. Yeah, but it's a valid complaint. So, right. I should also say that what large enough means in this case, and what large enough means for variables, the two things what we know is targeted people. Yeah. This threshold here for the local global principle to kick in is effective. Well, this one isn't. Okay. Basically, you see zeros. So, right. the context of this talk, maybe let me add here Linux name. Doesn't exactly establish things of this sort. It's very relevant for the ideas that we'll discuss. Okay. Right. Maybe actually, you know what? Let me say something now about what's tricky. Something that's tricky. So you can take just I'm going to write it more explicitly now. Taking this quadratic form here. So here's an exercise.
What is that?
Huh? This is a 9. No. Well, yeah.
Fixed number. Okay.
Yeah. No, I'm not. Yeah, absolutely. Okay. Yeah. So here's what you control. So this is not primitively represented. All numbers of the form for m squared, where n is positive, 0 to 1 more 3. It's not a terrible exercise. And it's curious, right, if you think this. So if you just look at this isolated as an isolated statement in the context of that question, really, then right, in particular, this is, oh yeah, and I should say, that locally these numbers are represented. Okay. And in particular, what you find, you find that that's a general feature here, is you will find the finite set of square clauses, without exception of what you want. All right. Okay. So
the set of exceptions is finite.
No, this is an infinite set.
Okay.
It's an infinite set.
No, but you say it doesn't represent all numbers. Does it represent some of them?
No, sorry. Let me specify the quantifier. Let me specify the quantifiers in less confusing manner. Any out of this form. Okay. Yeah. It's a nice exercise, actually. And the reason is, even though I won't, I'll put it on the board, but the reason is that the genus of this quadratic form has 2 spin genera. The other spin genus actually represents these. And it's actually not difficult to write down this quadratic form. Which has a very similar looking set of exceptions, but not the same one, of course. Good. So, yeah, this is to say, right, that whatever, that you need to rule out some square clauses in a statement like this. Okay, when n is equal to 3, not when n is equal to 4 or bigger. Yeah. Good. All right. So much for representations of numbers.
Just a silly question. Maybe you said what about n equals to 2?
That's a different. Okay. That's a totally different question. Essentially. It's a question clustered theory, not yeah. It's a different context.
But there's like no, is there like a local tool?
That is, I mean, this question does not make sense as phrased.
Okay.
Okay. So there is analysis of results when I'm representing quadratic forms. That's what I want to do next. Okay, so let me maybe give you one theorem just that have something on the board. It's exact. This is one of mine with my preventive with Shalom. Nabi Muhammad. Where we show something very similar to this. More precisely. So again, I'm in the setting, right? We mentioned it earlier, didn't write it down. I'm assuming that the quadratic form is definite. And I want to say that the global principle holds whenever whenever the codimension is at least 3. Okay. So here's the thing. So if Q is not really going to be presented and minimum okay. At the minimum of Q, it's going to be all non-zero values sufficiently large. Also, that is in that state action. Then Q is ridiculous. And so for the purposes of this talk, I would like to think of this codimension assumption here. Very much in the spirit of this codimension assumption, even though, of course, our tools are completely dynamical, to some extent, very dynamical. And yeah, you're very happy with the result. We mentioned, of course, it's not all the first work in this direction. Maybe yeah. So there is back with stick and Wieser. And the Simonyi use a completely elementary method to prove a similar statement when n at least 2 n is free. And then it took quite some time for this to be improved quite dramatically, actually. So this work was worked at Ellenberg connected fish in 08. Assuming codimension at least 5, okay? And they use homogeneous dynamics, just like doing this work. Okay. The novelty here is really an effective variant, whatever the input was on the homogeneous side, which is some sort of let me not say. Okay. Good. But right. begs the question.
Just Ratner is sufficient.
It's a Moses-Shaw type theorem.
But it's action of
This
two one.
Totally based on what Marina did. Totally based on what Marina did.
by all means.
Your name should be mentioned.
Definitely based on.
It's not a diagonal action, that's what.
It's not a diagonal action, which is what this talk is about.
Yeah, okay.
Yeah, thanks for that. Absolutely. Yeah. So we're passing. So we're going to ask basically the question if you can say something similar when the codimension is 2, okay, which is the limit of this method by what Konstantin was asking before. And dynamically, these two are completely different. So here's the new theorem. And maybe let me do it here, give myself some more space. So we're going to say something, and in contrast to this somehow, if you want to make progress on the diagonalizable things, yeah, the statements we're going to make are a bit more modest. So here's what we're going to say. So assume and restore then. So what we're doing is write this as I erased the typing. We're representing a binary form 2 variables by a form with 4 variables. Okay. And I'm going to assume something in addition. 2 things. I'm going to assume that the quadratic form of little q is primitive. Okay. And that on the following. If this specific number is going to be, it's a non-zero there. Let me write some random times, 5 and 11. Good. Then
That's great.
Hmm?
I thought you were going to say, you added mod 5 and 11, that's fine.
oh no, yeah, no, I don't want that would be very weird, right? Right. I'll explain this in a minute. Then okay, Q I'm going to write explicitly a lie here. And the minimum is large enough. Then this primitive goes. Yeah. So, good. So there are 2 conditions here that we didn't see before, right? These 2. Now, certainly the first assumption is a technical assumption. And I don't think it is intrinsically necessary in our method, but it's not obvious how to get rid of it. So in any case, I would ask you to ignore it for a minute. What this condition amounts to is basically having 2 fixed places, in this case 5 and 11. We will have, hopefully be clearer in a minute, interesting dynamics. Okay. These are linear, what we should call linear type splitting conditions.
Aber die werden daran zu fangen.
Very much like this.
Please take prime.
Right, you can take any two odd primes here, of course, like you definitely know. But the caveat is that what large enough means is going to depend on which two primes you take. Okay? Particularly, you won't be able to get rid of them by some magic trick. Okay. All right, so, okay, and I promised that I would elaborate on the lie here, which is very much related to what we were discussing over here. Okay? So the correct is a different problem. Correct assumption is basically the same. Correct assumption here is that little q is primitively represented as pages. Now, what is this spin genus? I'd rather not find it, but let me just say that this is the genus, okay? Spin genus is a further partitioning of this. Okay. And so I'm not a priori guaranteed, right, that whenever, so
Again, you really meant what you said, that the conclusion is that Q is.
no. I'm discussing the assumption, right? It assumes a bit more than
There's no local. This.
there's no local in this statement. It would be equivalent if the spin genus is the
No, but you
genus.
wanted to say Q is locally primitive represented by the spin genus, so.
No, what would that mean? Right, locally primitively represented by the spin genus is the same as just locally primitively represented. I'm assuming right from so the input you get from Hasse and Minkowski
I see.
is that one of the quadratic forms in the genus are going to primitively represent a quadratic form, little q. And I'm assuming more. I'm assuming that actually the spin genus is going to primitively represent.
Is this hard to verify?
Now, okay, in practice, right?
It's very painful.
It's very painful, yeah. But it's necessary. Okay, just to be clear.
But is it an algorithm? Is there a painful algorithm?
Yeah.
By the way, there's a very nice paper called Quaternary explaining these obstructions as integral Brownian obstructions.
Oh, okay.
They come from reciprocity at the level of the spin group. But he gave put it in a quite general context. He's got a paper with Winterberg, which explains all these square classes through that.
Okay.
So that.
First, if you there are cases, of course, where the spin genus is the genus. For example, if let's say that the determinant was square free, then the spin genus is going to be the genus. In practice, in particular, in some cases, it would be easily able to. This would just be equivalent to being locally primitive. What's also true is that much like in this example, outside of finite set of square classes of the discriminant permanent, being primitively represented, being locally primitively represented is the same. Right. Okay. Good. Okay, so maybe in the last 15 minutes, I want to say something about proof.
Just the one question. In Linux, when he did the case of 3, he had just one prime. You again,
Just one prime, and I want to, yeah.
You're going to explain why you're going to use this
Absolutely.
rigidity.
Absolutely, yeah. I mean, in a perfect world, we would also be able to use one prime. But yeah, okay, it's not where we are. And hopefully that's why. Okay, so
You also have both asymptotic on the number of
yes, I mean it's the same. It's almost optimal in the sense of what I'm about, right? Or yeah, as opposed to the statement that we had here before, that was very effective and much more general than what I wrote. This is a modest statement that's already was tricky to get to. Okay, so all right. Proof. Now, it's supposed to be, right, so the groups in dynamic center, so there's supposed to be a proof. Here's the group. Tracking what it's saying here, so I'm going to be taking G. It's going to be string group microdata. If you don't know what it is, I would formally what it is. This is the universal covered. It's that formula group. Okay. For all intents and purposes, capture some ideas. Pretend that it's your problem. Okay. So what's the correct space to look at? As it turns out, of course, you could look at the real portion of this. That's a vector space, right? Because in particular, right, we were assuming that the quadratic form is positive definite. So this is just a portion of a compact group. There's nothing interesting happening. No dynamics that is interesting. The correct space turns out to be the other portion. Where the dells here is, well, I'm trying to capture all completions of Q. Okay, so I'm taking basically the product where I need to restrict in order to get the ring. And okay, that's a huge space, particularly where I can act on by not just the real points of this group, but also Q2, points of Q2, points of Q3, etc. And it sits above, in some sense, it sits above this silly quotient. Okay, but not just that one. It sits above all similarly defined quotients. That's in QI, where these QI here are precisely the other guys that I see in my stages. In other words, this valid space that is very large and has many interesting actions, sits above a disjoint union of these real quotients. Okay, this partition this partition so the parts of this partition might have good. So I'm going to do something maybe intuitively confusing, but I think a lot of it. I'm going to do is we're going to say we're going to assume that we have a sequence of quadratic forms. 1, 2, okay. With, well, certainly the minimum is supposed to go to infinity, right? That are primitively represented. Okay. And we're going to show, instead of what we actually wanted to do, right, we're going to show that that these, when the minimum is sufficiently large, they are represented by all of these quadratic forms. In other words, that yeah. And let me tell you what that means in terms of this homogeneous picture. Okay. Right. So I have a primitive representation. We were saying that primitive representations correspond to two-dimensional subspaces, right, of this four-dimensional rational space. And so take one of these. Okay. So taking Ti, yeah. Going to be the stabilizer such a representation. For all intents and purposes, this is basically SO2. Okay. Sitting inside what is basically an SO4. Okay. And what's the goal? The goal is to show that these so I have a pose, okay? It's a one-dimensional group, and I can look at the orbit of such a thing, right? Inside this huge metallic space. And my goal will be, well, corresponding to this picture, right? The fact that we wanted to find representations of these by any element of the spin genus here, okay? It will be to show that I hit any open set in that partition, okay? These open sets, okay. Or maybe a fortiori, seeking asymptotic events. So my way of saying that whenever I take an open set, sufficient for a sufficiently large I, this orbit will hit that open set.
But you don't have an equidistribution thing?
No.
Interesting.
What we have is we'll actually show that the measure on these is has a hard component. Right, this text will show that Y is the uniform measure. On maybe it's called by I. So the measure invariant on the full course. Then any star limit mu is at least delta of measure on full spectrum. This is the value of the delta. Okay.
Yeah, there's a number you could write 0.01 or something.
Yeah, I think also in practice depends on the minimum of the quadratic form. In the interesting case where these are balanced, 0.3, something like that. It's quite a chunk actually. You do get quite a bit of. I'm coming back to what Peter was saying before. You would like to have delta equals 1, right? But this is not what we want. So, what goes into this? So the observation that you make is that this could be step yi, right? It's invariant on the remind myself which band that shows 5 and 11. On the Q5 points and Q11 points. Okay. So both of these, by assumption, this is what one needs to clarify that, it's an easy exercise. This condition translates into big benefit to the fact that these are actually non-compact. So, in other words, if you want to translate what that condition means, is that I am making sure that I have 2 primes at which I can use dynamics, 2 fixed primes at which I can use dynamics. So, right. Okay. So I'm doing what happens often. I'm going to the limit. I will have from this interesting invariance in the limit. Okay, and I'd like to show that measure actually satisfies some rigidity in this sense. Okay. So what we actually show, let me give you some apostrophes, is that any such weak star limit mu has entropy strictly bigger than a half. Let me write that. Comes to maximum. Entropy, so it's an imprecise statement on purpose, but basically you can take any element for one of these 2 tori, look at what the entropy is and prove such a statement. Okay, maybe on bound. Now, okay, this doesn't seem very tangible a priori. Okay.
Once you have positive entropy, don't you have that something homogeneous or by Elon's work?
Yeah, you do get something, but there are intermediate objects.
Yeah, I understand. I understand why you want to get bigger than half.
Yeah, exactly. Yeah.
But I'm just saying that
so getting positive
you already do have positive entropy to get some knowledge of what the limits could be.
I mean, getting positive entropy is usually easy, right?
I know Hellenic does. Is it the same?
Here, yeah, it's very similar. I mean, in fact, you would get in a rather trivial manner, basically, well, trivial is not correct. In Linux manner, you would get precisely half it's not too surprising. So
If you are sort of immediately estimating the number of different orbits by the mass formula, that's what Linux does secretly. He's solving x transpose AX equals B and giving an upper bound for, the angles must be, you're using that.
Let me give you exactly what the statement is that we prove, which is very similar to what you just said. Okay. But maybe before I do that, let me mention that. So so if you apply and also pick the right words, the names on the board, so it's what we can apply here and then assuming just here with some very good results. Of my lines. With a very specific particular to the situation that we're in, which is so spin Q here is basically, or at least on the complex numbers, something like S and times S. This is the situation which results that I didn't write here to apply. Okay. So I think it's very pleasant that these results are applicable in this instance. And so particularly we go from here to here. Now, what this translates to, if you want to get your hands dirty, is the following. This entropy statement translates to a counter statement, very much in Linux spirit. So looking at quadruples, and these are vectors in Z4, where following through, I'm supposed to, each of these two are supposed to be a representation of my quadratic forms. Okay, taking definitely, yeah. This is supposed to be true. Yeah. And I'd like to have some condition as well what it means to be close. Okay. This is a bit trickier. I require the W1, so that's the first vector in the second representation. Okay, it's congruent to k times V1. It's congruent to k times the mod 5 to 10. Okay. But for some rotation in the plane V dot in the plane spanned by V. Okay, so I put this down again. Some counting pairs of representations that are close together. Okay. Close together, but of course not the individual basis vectors, but rather up to some, this closeness is true up to some rotation. Okay. And right. And so you're supposed to get a bound on this set, okay? And so I'm out of time. Let me say one word about how we do this. Basically, what you want to do is you want to look at the quadratic form on the span of these vectors, okay? Which turns out to be, set aside some restrictions, certainly. And in fact, the quadratic form itself captures basically by some application sigmas for essentially all the information that you want. Okay. One fact, the crucial insight that we have here, I would argue, is that if you look at the determinant of this quadratic form, okay, which you can see as, well, it's certainly going to be polynomial in the inner products of these vectors. Okay, is actually, of course, not too surprisingly, the square times the determinant of the big form. Okay. The square condition is what we need to leverage that improvement.
Say determinant method, you mean like the Keith Brown Peeler?
Yeah.
Yeah, it gives you an upper bound, which is enough to get the extra delta.
It's, yeah, basically, if you just completely ignore the square condition, you'll get precisely half.
Which exact theorem you're quoting there, or you're proving a new? Or in that variety, you're quoting?
Basically, we're quoting basically Bombieri. Turns out to be enough.
Wonderful.
All right.
Also using a new, it's not some kind of, it's not one of the old theorems, it's a new theorem of Manfred and Mine that didn't have mass application so much. Also something which is nice.
Yeah, well, where's Peeler when his work's being used? Oh, wonderful.
All right, good. Yeah, I'll stop here. Thanks.
Thanks.
What's your delta?
So, okay, there is really, truthfully, there's no argument here on stage. Is basically if you somehow, if you minima grow, say logarithmically in the discriminant, you don't want to apply this entropy argument exactly. So there's a game. Now, in the extreme case, which is the most interesting one, where the minimum is basically as big as possible.
What do you mean that is possible?
Like square root of the discriminant.
The positive.
Then in that extreme case, the delta is roughly 0.3 or so. No, sorry, in this no, 0.1 right in the compensation. It's sizable, I would say. It's not actually small, but it's quite a long way from optimal. In fact, if it was optimal, you would in particular be able to get rid of one of the primes. I think you had a measure of maximal entropy, like in Linux. Yeah, you wouldn't need these nice mesh classification results.
Well, Ron can answer this, but doesn't that work give you that when you have positive entropy, that the intermediate measure has to be somehow homogeneous? Am I
So
wrong?
the intermediate measures in this.
In other words, why doesn't the delta bigger than 0 jump you up to 1, 3? Am I confused?
So, yeah, okay, I can answer that. Basically, what you don't know is that if the measure here by some miracle was ergodic,
Yeah, then you can.
then you would, I mean,
Absolutely continue.
very much. But this is not what you know, of course, right?
I see.
Yeah, you have to, yeah, you end up taking an ergodic decomposition, and then some of these ergodic components
Okay.
are, have large entropy.
Yeah.
Your argument can't show that any ergodic component has this large.
No. So the thing is, yeah, I mean, if all ergodic components have this much entropy, well, then all ergodic components would be the hard measure, and you will be very much, you will be even happier.
But you can't say that.
Yeah, I cannot say that.
I don't know. I mean, the points are far apart. Can't you only take those that correspond to one ergodic measure? Or?
Not clear to me how.
Okay.
We can discuss it. I don't see. I don't see it.
What is the flavor of the Bombieri-Peeler application that you're looking at? What kind of equations?
So, right. So I mean, basically, you end up writing down a variety. In this case, it's going to be some variety that looks like roughly looks like this. So x0 squared is some polynomial, and f is degree 4. Now, it's a counting statement on a variety that looks like this. Of course, you have,
And the variables in
basic conditions.
so sort of a weighted homogeneous variety. I mean, so the variables in x1 up to x4 in a box of size h or something. And
It's, in the most interesting case, yes. Absolutely. But yeah, I mean, this is not the, in fact, this distortion is actually quite relevant to us.
okay,
And what's the upper bound you need? You need an upper bound on the number of points in the box.
Basically, an upper bound to this. So I didn't give you any.
Brown and Lillian Pierce. They
wouldn't be-
study these square sieve they give.
From what I understand, that wouldn't be enough to get you. In particular, I didn't give you the full picture here. Actually, you need to translate what this Kalman's conditions mean. It's going to be some polynomial relations in the variables multiplied to the something.
I mean, how much do you need to save to get a non-trivial result?
Just a little bit. Essentially, whenever if I completely ignored this equation, right, and all I did was count. Let me tell you what these variables are, because it's not actually too hard to see. The variables here are basically inner products of these vectors. So v1 in product w1, v1 in product w2, etc. Those are the variables. And if you just follow, if you chew long enough on these common relations and the obvious bounds, just Cauchy-Schwarz, just those get you to half. So any little bit that you can prove on, will actually give you delta that you're looking for.
Good. If Bob Horn were here, he would say that Gallagher's largest sieve actually does better than Bombieri-Peeler work in many of these problems where you're just detecting a square.
Okay.
So I think that Hilfran has I think the strongest for square equals a polynomial is they wrote in a paper where
I know.
they're doing worse than large sieve.
Well, Gallagher's largest sieve actually
Does better.
Yeah.
They don't know that.
And this seems to have been overlooked by the
Oh,
many
okay.
reviews of the
Right.
other systems.
My apology on that. Sarah is the first to, in these kind of problems, he also highlighted a large sieve in his book.
Right.
In that. I mean, there are many ways to get non-trivial bounds. He and I are trying to understand just exactly what you need.
Yeah. I mean,
So non-trivial bound is very, depends what you're calling non-trivial also.
some trivial, so it's particular, it's with a power setting. Right?
Yeah, they all give a power set.
Yeah. I mean, in the end, somehow it's not it took us a while to stare down the exact correct way to do it, but it's completely elementary.
If there are no other questions, let's tackle this again.